key instrument I used in my PhD research is called the epistemic plane. Now, the different quadrants represent insights, ways of thinking. Simply put, fixed, defined, or what we call strongly bounded phenomena with standardized methods, like most of the natural sciences, need what we call a purist insight. Now, we often call these things fundamentals or foundations or principles. Now, fixed procedures, irrespective of the concepts or phenomenon, need iterative practice, and we call this requiring doctrinal insight, whether it's mathematics practice or handling specific kinds of tools. Now, when we move to the top left quadrant, we're talking about needing situational insight. Now, the phenomenon is clear, what we want to do, but there are multiple ways to do it. Now, the situation will dictate or guide decisions as to possible approaches. Now, this bottom left quadrant is about something other than knowledge. It's about context. Now, most of our university teaching happens on the right-hand side. Well, quite simply because it's easier to assess and it's more standardized. Now, what industry keeps asking for is graduates who can work on the left-hand side in the space of possibilities, where there are multiple possible approaches and where there are very different contextual features, different stakeholders. Now, what we do know is that real-world problem solving actually means code shifting, recognizing what kind of knowledge and what kind of practice you need at different moments in different contexts. Now, moving from fixed to open-ended approaches or from strongly to weakly bounded concepts, what we know is that we need to enable this kind of code shifting. Now here, working with my colleague Coral Kruger, he's used this epistemic plane to design and implement a strategy to improve control systems teaching, shifting between lab and virtual practice in a way to stretch students into more open-ended problem solving. There is another example of the use of the epistemic plane in the chemical engineering module. When mapped onto the epistemic plane, what we see is that this lecturer, my colleague Lydia Rett, explicitly enabled students to code shift from the conservation of mass and energy principles to the equations, to the use of software, bearing in mind the context of their specific projects. And she did this in an iterative, cumulative fashion. We've used the same principle of the epistemic plane to unpack the graduate attributes, as well as to design the student learner management system, the user interface, and how they're engaging with the different insights that they need. I've even used the plane to look into our students' experience of an enriched curriculum. Now, ways to expand our students' awareness of the rich contributions from our continent. Examples such as Samira Musa from Egypt, who developed the equation to break the atoms of cheap metals, making the medical applications of nuclear technology, such as X-rays, more accessible. Or Ibn al-Haytham. Now, he documented his use of the scientific method 700 years before Newton. Jamila Abbas, for example, from Kenya, saw that small-scale farmers were being taken advantage of based on their lack of bargaining power. She created a simple mobile phone platform to provide critical information to small-scale farmers so that they could organize themselves and pool their resources to act as commercial farmers, leveraging the advantages of commercial market positioning.